So we're talking about the magnetic force on a charged particle. So we have a magnetic field. I've made it uniform just to make it easier. The magnetic field symbol is B. And then last time what I did was I dropped a bunch of charged particles into that field, and I saw what it takes to feel a force from that field. We found that either if the charge is at rest, it's moving parallel to the field in the same direction or parallel in the opposite direction. Sometimes we call that anti-parallel, just to distinguish they're along the same line but in opposite directions, not to be confused with perpendicular. So if we have the charges at rest, parallel or anti-parallel to the field, then there's no force. So in that case, the magnetic field will not exert any force on the charged particle. It'll just obey a trajectory under Newton's law, Newton's first law, which is just, it'll keep doing whatever it's already doing. We found that an essential ingredient for feeling a magnetic force from a magnetic field is to cut across the field line either in whole or in part. So if I have this charged particle which is perpendicular, it's given an initial velocity perpendicular to the field, it will feel a force. That force, which I'll show you how to get this direction in just a second, but it is into the page. So we symbolize into the page like that. So it will curve into the page. This is the first truly three-dimensional topic we've done in Physics 1 and Physics 2. So we need to symbolize directions that aren't available to write on the plane of the board. It doesn't have to cut exactly across the field lines. It can just have a component that cuts along the field lines. So in general, if you shoot a particle at some velocity like that, it can have components both parallel and perpendicular to the field. And it's the perpendicular component, if it exists, it will result in a force. So the law for the size of the magnetic force is Q V perpendicular times B. Okay? So notice that in contrast to the electric force, where you just multiply the electric field times the charge, it has that one little extra ingredient that makes all the difference. It's that V perpendicular. So that introduces into the situation some kind of dependence on the motion of the object. In the electrical field, there was no dependence on that. You could count on positive charge feeling a force downstream to the field, negative charge feeling a force upstream to the field, regardless of how it was moving. But now, we need to consider something about the motion. I guess let's briefly take a look at the units. Well, of course, electric field was measured in newtons per coulomb. We occasionally also refer to it as volts per meter because that's equivalent. But in this formula, I think it's most useful to think of electric field as newtons per coulomb. It tells you how many newtons of force are available at a particular location in space per coulomb. Then we multiply by how many coulombs we put there, and we arrive at newtons, how many newtons of force it feels. So this should be old hat. So let's similarly analyze our new force formula. It's going to have give us the ability to find out what are the units of magnetic field, because we know the units of everything else. So if we take a look at this formula, we can solve for the units of magnetic field. That'll be the units of force over the units of charge and velocity. So what do we measure force in? Newtons. What do we measure charge in? Coulombs. So far we just have the same newtons per coulomb, but of course the extra ingredient is the velocity. So what's the units of that? Meters per second. So the units of magnetic field are newtons per coulomb, meters per second. That extra ingredient kind of makes it a little bit of a weighty alphabet soup there. And there's only, I mean, we could condense it down a little bit. We could take the coulombs per second. We do have an abbreviation for that. What's that? What do we call a coulomb per second? It's an amp, right? It's units of current. So you could call it a newton per amp meter if you wanted to. That doesn't really condense it down enough for our tastes, so we just rename it. It's called a Tesla, or capital T for short. So the units of magnetic fields are Teslas. Okay? Well, 1 Tesla magnetic field is actually quite a large magnetic field. for instance, in an MRI machine where they generate this very, very large magnetic field. It's on the order of a couple Teslas. It's kind of like a Coulomb. It's not really an everyday amount. It's a lot of magnetic field. But that is the SI unit we have. So, a couple different things. Are there any questions so far? Just units or whatnot? Yeah?
Is Tesla for Nikola Tesla?
Yes, it's named after him. We'll talk about him a little bit later. So a couple things I want to do. Obviously, the right-hand rule to figure out the directions is going to be a whole discussion in and of itself. But one thing I do want to do before I do that is I want to put a few bells and whistles on the force formula. And the reason I want to do that is because identifying the component of the velocity that cuts across the field line, right now we would have to do a SOHCAHTOA every time, right? We'd have to carefully say, was that V cosine or V sine theta? And what I want to do is do that SOHCAHTOA once so we never have to do it again. So incorporate it into the formula so the formula doesn't require or doesn't rely on you accidentally or doing the SOHCAHTOA correctly or accidentally messing it up. So I'm going to call this theta, and then this is V sine theta. So my formula for the magnetic field is going to be Q V sine theta times B. Now, anytime someone tries to do a SOHCAHTOA and work it permanently into a formula, you guys, of course, know at this point that one person's cosine is another person's sine. It all depends on how you break it up. So if I had instead chosen to break it, instead of like, I guess I'll draw it separately because it's getting messy. So if I had instead of chosen to doing it like this, where this component is V sine theta, of course the other option I would have had would be to break it in up then over, like this, right? Up first, then over. Then I would have been using phi. And then if I were using phi, which is the complementary angle to theta, this component that I'm interested in would have been V, whoops, that's the adjacent side, V cosine phi, right? So is it cosine or sine? Well, theta is a special significance and phi does not. And here's what that significance is. If you look at the magnetic field, theta is the angle between the velocity and magnetic field, and phi is not. Okay? So as we work this sine function into the formula permanently, there is going to, of course, be a very specific way of choosing theta so that you can count on it always being sine and never cosine. So let me write it like this. QVB sine theta. So I've just taken the sine on the outside. All those parentheses don't matter. These are all multiplied. And it is always sine if you choose the angle to be between B and B. Okay? And this might be a good time to remind you, what does it mean when two vectors are, we're talking about the angle between them. What we're talking about is the angle between them when they're placed tail to tail. Okay? So it's really important to place them tail to tail, follow the rules of how these angles should be measured. So don't put them head to tail. Head to tail is what you do for vector addition. We're not adding these vectors. In fact, it should be pointed out that these vectors aren't even addable. You can't add a velocity to a magnetic field. They're apples and oranges. It's like adding a meter to a second. It has no meaning. We're not adding them. We're measuring the angle between them, and when we talk about measuring the angle between two vectors, there's agreed upon rules for how to do that. You place them tail to tail, and you measure the shortest angle between them. So, tail to tail, and it's the shortest angle between them, which means that this can run only from 0 up to a maximum of 180. That's the range that two angles can make to each other. The angle is 0 degrees if they're pointed exactly the same way. Then it can grow 90 degrees, of course, is like this. And the maximum angle they can make is 180, like this. The angle can't get any bigger. Because if you kept on going, well, if you're measuring the shortest angle between them, now you should be measuring it the other way, right? So the angle's actually closing again. Okay? So those are the rules for talking about the angle between two vectors. And if you measure the angle in that way, this will always be sine. Okay? This is intended to make it easier for you to not have to do SOHCAHTOA when you're dealing with this. We should give it a try. Let's do the various cases. If theta is 0, it looks like this. The charged particle points the same way. It's fired in there, the same direction as the magnetic field. What's sine of 0? 0, so the force is 0. So that we already said, okay? That when you fire something parallel to the magnetic field is 0. Let's do the other case, if theta is 180. Then you fired it anti-parallel. Same line as the field, but in the opposite direction. What's sine of 180? Also 0. So this formula seems to be encapsulating what we needed to. And, of course, the third case we might look at is 90 degrees, where we fire the particle directly across the field lines. Well, sine of 90 is 1. So that's the maximum amount of force we can get. So the amount of force will be the charge of the particle, its speed times the magnetic field, and there's no pesky sign there cutting it, or watering it down, cutting it down the sides of it. You get as much force as you can with this particle at this speed and this field, because of you've fired it directly perpendicular to the field. Okay? So these are your three cases. And so what I would suggest to you, this is definitely the kind of the handy form of just getting the answer as quickly as possible. The ingredients are what's the charge, what's the speed, what's the strength of the field. It's always sine, never cosine, and the angle is chosen in that way. So that'll just get you the answer quickly. I do like, however, to keep this in mind, because that's much more conceptual in the sense that it reminds you that you have to have at least a part, if not your entire velocity, cutting across the field lines perpendicular to it before you get any force. Okay? So they both have their strengths and weaknesses. This is nice and conceptual, but it would require you to do the SOHCAHTOA. So let's do the SOHCAHTOA once and never have to do it again, and this is a user-friendly form to go with. Okay? Okay. Are there any questions about the size part before I move on to the direction and talk about the right-hand rule? Okay, so let's do the right-hand rule. So the right-hand rule, the orientation that I've drawn here is not really where to get started. So what I want to do is start us off with something a little bit more straightforward. Let me have that the magnetic field is into the page. And it's uniform. So that would look like this. As you will see, choosing the magnetic field to look like this will help us to keep the trajectory of the particle on the page, so we can practice the right-hand rule a number of times. So let me put in the particle like that. And hopefully you are convinced that this will feel a force, because this particle is certainly not moving parallel or anti-parallel to the field, right? If it were moving parallel to the field, it would be going into the page. If it were moving anti-parallel, it would be coming out of the page. It's actually going to experience the maximal amount of force. It's cutting across the field lines in its entirety. So here's how the right-hand rule works. And I should mention this is a mnemonic. I think there are at least 5 different versions of the right-hand rule that I've seen. I'll show you my version of it. That's not, I didn't make it up, but it's one that I prefer. You may see others, and if you want to use one of the other ones, if you like it better, if it makes more sense to you, then use that. So I use what's called the slap rule, okay? This is the slap version. So here's how it works. You use a mnemonic to figure out the force as follows. What you do is you imagine slapping V into B with the palm of your right hand. It's important that it's the palm, it's important that it's your right hand. And if you do that, your thumb will point in the same direction as the force. And the key thing to remember is that the force will be perpendicular to both the other two. So it should be noted that V and B don't have to be perpendicular. You are entitled to throw a charge into a magnetic field however you feel like. If you feel like throwing this is not always 90. The V and B don't have to be 90 degrees. In fact, that's why we have the sign of theta here, because that theta could be anything. What I'm saying is that the force has to be perpendicular to both of those. Okay? So if V and B form a plane, the force is perpendicular to that plane. So let me show you. Okay? So you take out your right hand. You point your fingers along with V. So V's like this. Now, of course, your fingers are along V no matter how you rotate your hand, like this, right? This is like the beauty queen handshake, right? Your fingers are pointing upward, right? But your palm can point any which way. But you want to make sure that you orient your palm so that you can slap V into B with the palm of your hand. Now, B is going into the page, so I want to position my palm like this so I can slap V into B like that. So slap V into B, force will be like this, okay? So that's the direction of the force. Now, if you want to visualize that, you can visualize it like this, okay? You're basically trying to imagine this thing. So what you have here, this is V, okay? This is the velocity of your charge. This is B, okay? This is the magnetic field. Notice that these two can make any angle you want to each other. You can throw it in like this, like this, like this, however you want. But the force is always perpendicular to both of those. So this is the force, okay? So what I'm trying to do is imagine, if I can get this to not fall apart on me. What I'm trying to do is imagine this. I'm trying to take my palm of my right hand and slap V into B, thumb gives the direction of F. So it's just basically visualizing this in any orientation, like any orientation you're trying to imagine it. So there's lots of different ways to go wrong, okay? One of which is like this, you do the slap, okay? My thumb points that way. I can't slap with the top of my pointer finger, okay? It's with the palm. So that's my palm is underlined. You got to use your palm. So use the palm like that, okay? Another common mistake, like that. Wrong way. You backslap. There's no backslapping. You got to use your palm, okay? Here's another common mistake that I often see, especially during exams. Go here, you slap with the palm. That looks good. The force is down, but the force, I get my thumb is down, but the force is up. What did I just do? I'm using my left hand. It's called the right hand rule, okay? You will get opposite answers if you use the other hand. You notice that if you slap something into something with the palm of your hand, you'll get opposite answers. So this is where one of the few times in life where left-handed people have a real advantage. So you can be working on your exam and doing the right-hand rule at the same time. Okay? But if you're right-handed, work on your test, pencil down, use your right hand, pick it back up. Okay? So it has to be the right hand. So it has to be the right hand because that's how this mnemonic was developed, right? So if you can think of another mnemonic that doesn't involve your right hand at all, but always gives you the right answer, use that. Okay? So let's keep practicing. This thing will not go straight anymore because, of course, it's been deflected. So let's go over here. It's deflected like this. Now it's going this way. Let's practice again. So I point my fingers along V. V is now to the left. Okay, and now I have to decide how to orient my palm to be able to slap V into B. Again, here's another common mistake. V into B. There's nothing going this way. The magnetic field is not coming out. Okay, so flip your palm around and slap V into B, which points into the page, and the force is going to be down. Okay. And remember that, I guess I should have drawn it here as well, remember that the force comes out perpendicular to both of the other things. So the force comes out to be perpendicular to the velocity. And it should be pointed out that if I'm able to draw the force on the plane of the page, then it's going to be perpendicular to the magnetic field, because the magnetic field is perpendicular to the entire board. Okay? So this thing will not go straight, it will be continued to be deflected. Let's practice again. And by the way, you guys have an advantage that I don't. If you find yourself going into some arthritic contortion, just rotate your page. Your page is mobile, okay? Rotate it into an orientation you like better. Write down the answer, then rotate it back. I don't have that advantage because I can't take the whole whiteboard. So I'm going to have to do it in this orientation. Point my fingers down, and then I slap V, which points down, into B, like that. So the force will be like this. And you can kind of see where this is going already. What kind of trajectory is this particle going to make? It's going to make a circle, right? If the magnetic force always comes out perpendicular to the motion, then it's going to just wrap it into a circle. I guess let's confirm one more. So I'll practice. So V points to the right. I figure out how to orient my palm such that I slap V into B. B is into the page. So I slap V into B. Force is up. We'll do lots more practice on this, but hopefully you get the basic gist. Okay? That's the right-hand rule. So first of all, one of the things that is fairly obvious next course is to figure out what are the properties of the circle that are being made. So here, we can set that the actual amount of force, which is FB, is apparently meeting the requirements for circular motion. And what do we call that requirement? Does anyone remember what it's called? Centripetal. So the magnetic force provides the centripetal force. So let's kind of use this as a jumping off point to calculate the properties of the circle. We'll put in, here's our formula, QVB sine theta on this side. And then what's the formula for centripetal force? Does anyone remember? mv squared over r, that's right. So if you want to take something in a circle, the amount of force that will be required depends on the mass you want to take in a circle, how fast you want to take it in the circle, and the radius you want to take it in. So let's solve for the radius. That might be something instructive to discuss. I guess the first things first, what should be the theta? What theta do we put in the formula? What's the angle between the velocity and the magnetic field? Is it a constant? Even this thing is going around?
90 degrees.
It's always 90 degrees, that's right. Even as this thing circles around, it's circling around the plane of the page, and the magnetic field is perpendicular to that plane. So this is 90 degrees at all times. And sine of 90 is 1. So we get that this particle, even as it's deflected off of its initial trajectory, it stays perpendicular to the field. It circles around the field lines. We can cancel off of V. Let me go over here. Let me clean it up so far. QVB equals mv squared over r. Of course, I have a speed on both sides, so I'll cancel that. And then I'll just solve for r. That will be the radius of the circle that it makes. So if you shoot a charged particle with some speed into a magnetic field in this manner, it will curve into a circle, and this will be the radius of that circle. It depends on the mass of the object, it depends on the speed of it, it depends on the charge, and it depends on the field strength. This is probably one of the most useful formulas that is not on your equation sheet, so you should definitely know how to get it, okay? Now, of course, you'll find the magnetic force formula on your equation sheet. You'll find the centripetal force formula. So really, I don't think it's too much to ask you to set them equal and solve for r, okay? So I don't want to give you everything too pre-cooked, okay? I want you to understand where this radius formula comes from. And not only do I want you to be able to get it, I want you to have some kind of intuition about what are the different ingredients and why they matter the way they do. Let me take a look at each one in turn and find out what's going on. So first of all, this would seem to indicate that if you have a more massive particle, what happens to its radius? Increases. They're directly proportional. If you have twice the mass, it'll make a radius that's twice as big. Now why does this make sense conceptually? Well, if it has more mass, it has more inertia, right? It's more stubborn to curving. Well, that means that it makes wider turns. It makes more gradual turns. More inertia means more gradual turns. If you look at where the mass comes into the equation, the mass comes in only on the right-hand side. If something has more mass, then it's harder to take in a circle. It has a bigger requirement. But there's no mass on the other side. The magnetic force does not depend on mass. So the magnetic force kind of is what it is. You get the magnetic force based on your charge amount, your speed, and your field. The magnetic force kind of is what it is, but if you have a lot of mass going on with that, then that amount of force is not able to curve this thing into a tight turn. It actually goes into a much larger, more gradual turn, just because the object has a lot of inertia. Let's take a look at the charge. If you increase the charge, what happens to the radius? What is it? It decreases. So if a particle has more charge, that means that the magnetic field can take hold of it more strongly, and it'll make it turn into a tighter turn. That's if the charge itself is larger or the magnetic field is larger. That will mean that the particle gets pulled harder by the field, either because the charge itself is larger or because the field itself is larger. You'll grab that thing and pull it into a nice tight turn. The final factor is a little bit more tricky. We find that as the speed goes up, what happens to the radius? increases. So if you fire the charged particle into a magnetic field at a faster speed, it will make a larger circle. Now that may seem counterintuitive with the point I just made, because we said that if you're going faster, the magnetic force is larger. So why is it that the magnetic force doesn't take hold of this particle and make it go in a tighter turn? Just like for these reasons, right? If the charge and magnetic fields are larger, the radius goes lower. So why does this seem like it goes the opposite? Well, here's the thing. If you double the speed, you will double the magnetic force. If you go twice as fast, then this will be twice as large. Here's the problem though. If you go twice as fast, yes, you get twice the magnetic force, but guess what? How much more force do you need to hold that turn? 4 times. So the centripetal force is 4 times the amount. This is what you get, but this is what you need. So what happens when you don't get what you need? You fly out. So that's exactly what happens. If you go faster, if you inject this charge at a faster speed into the magnetic field, it will make a larger turn. Yes, the magnetic force increases, but not as much as it needs to increase, so it still flies out. So that one's tricky, of course, because V does appear on both sides, right? So it's a matter of which side is it more important to, okay? So this right here explains why is it that the radius gets bigger, even though in some sense you might think, shouldn't it get smaller? Okay, so that's one important thing when we have a charged particle that is in a magnetic field. It can make a circle. And one of the other things I do want to point out, if the force is always going to be perpendicular to the motion, it's never going to be with the motion or never against the motion. It's always going to just guide this thing along, okay? So the magnetic force is always perpendicular to the motion. It's never with it. It's never against it. What happens when a force acts in the same direction as the motion? What does it do to the object? Speeds it up, exactly. And what happens when the force is against the motion? It slows it down, right? So it's never with the motion to increase the speed. It's never against the motion, so it never decreases the speed. The role that it plays is just as a guide. I call these in Physics 1 guiding forces. So they change the direction of motion, but not the speed. It can channel this thing into a circle, but you will find that as this thing circles around, it never does it any faster or slower. We have a fancy word for this course in Physics 1. We say that forces that are perpendicular to the motion do no work. So the magnetic field cannot do any work, and of course, instead of talking about speed, we talk about a quantity called kinetic energy, right? So if something can't do any work, it can't change the kinetic energy of the particle, right? So the magnetic force is deflective only. Deflective only. That's the only thing it can do. It can take whatever pre-existing speed you have and deflect it, but it cannot make you go faster or slower than you were going before. Okay, so let's go back. I purposely tried to leave these here. These were from earlier today. Let's first of all practice the slap rule and make sure we can get these answers. So here, it's not in the plane of the page, or I should say that the magnetic field and velocity are in a different orientation than before. So let me try it out. Here's my V. I point my fingers with V. I try to figure out how to orient my palm to slap it into B. B is now that way. This is the magnetic field. So I slap V into B, right? V slapped into B, the force is into the page. And that's, of course, how I knew that, okay? I can also try with this particle. This is our first time where the angle isn't 90. It's a short slap, right? So V slapped into B. It's a pretty short slap. It's less than 9 degrees. Thumb is still in, right? See that? You could have, I guess, something like this. That would be a long slap. I'd have to go like this. Long slap. Right? You see that? B, B, force is still in. And of course, the reason the forces are the same in all three of these cases is because if you look at the part that matters, which is V perpendicular is pointing exactly the same way in all the three cases. The only thing that's different about these three is in this one, V parallel is nothing. There is no component of the magnetic field that is, or component of the velocity that's with or against the field. Here, V parallel is with the magnetic field, and here V parallel is against the magnetic field. But remember, V parallel doesn't matter anyway, right? The reason why the magnetic force exists is because you have V perpendicular. V parallel doesn't really affect the magnetic force at all. However, it does affect the trajectory. So what we should do is we should talk about what are the different possible trajectories in our various cases. So let's do that, make it kind of a roadmap to go forward. So let's make a little chart that says, do you have V parallel? Do you have V perpendicular? What is your motion? So the first thing, which is quite boring, let's say you have neither of these. So if you don't have any velocity either perpendicular or parallel to the field, what are you doing? What is this particle doing? Nothing. It's at rest. This particle stays at rest. So again, remember we characterize the magnetic force as deflective only. It can't increase or decrease the speed. It can only deflect the motion that you already have. In this case, we don't have any motion, so there's nothing to deflect. So there's no magnetic force at all. All right, the next case, we don't have any V perpendicular yet, but we do have V parallel. So what are you doing here if you have V parallel? How are you moving? You're either moving parallel or anti-parallel to the field. And what do we say happens then? There's no force. So you just basically stay at constant velocity either with or against the field, whatever direction you initially set it in, right? I guess I should expand this. So these first two states are really just consistent with Newton's first law. I guess I can write that over here. Newton's first law. And of course, the reason why we haven't had any action yet is because we have not allowed V perpendicular to kick in yet. That's where the action comes from. Having your velocity either in whole or in part perpendicular to the field is where you get your force. So let's do the next one. Let's say no V parallel now, but we do have V perpendicular. So we just saw, what does the motion look like for that? It's a circle, that's right. And we saw that the radius of it was equal to this. And then, the obvious final case we have to talk about is what if you have both of them? Well, that's just going to be a combination of the last two. You're going to go in a circle while staying at constant velocity with or against the field line, however you set it. So you think about it, right? If you have this be perpendicular, that's going to cause us to curve in a circle. We saw that initially the force is into the page, so it's going to curve in a circle like this. But what if you also have a V parallel that you just stays there, it doesn't do anything? What kind of motion is that? Corkscrew. It's a corkscrew or helix, right? It could either corkscrew downstream, because you happen to throw it with the downstream component, or if you happen to have it corkscrew upstream because you happen to have that there's a component against the motion. But either way, it'll be a helix. You can spiral around the field line downstream or upstream. The drift upstream or downstream is just how you set it. The magnetic field has nothing to do with that. But it's the magnetic field that causes it to corkscrew. So it's a helix. So what are the properties of this helix? The radius. The radius will now depend entirely on one component of your velocity because the other one has no bearing whatsoever on the magnetic force. Now that's a tricky formula to get, so let me briefly mention how to do that. You do it the same way. You set the magnetic force equal to the centripetal force formula. And here, just for convenience, I'm using the shorthand for the left-hand side. And here you have to really watch out. Because this is the first time, it'll be the first time and the last time, where an object is going in a circle, but the circle is not all there is. A circle is not the whole motion, it's a part of the motion. So the v here, that's the speed at which you go in a circle. That should be v perpendicular. It seems weird to take only a component and put it in there. But remember, that's the component that's circling. There's another component that has nothing to do with the circling. It has to do with the drift. So if you remember that, and again, that's a tough thing, so I'm just telling you what the answer is, you will get that for the radius. What about the other part? Well, how far are you going to go upstream or downstream? There, you can just use distance equals rate times time, right? So there's this other component that the magnetic field has no effect on. How far are you going to drift upstream or downstream? Well, it just depends on your rate in that direction and how long you're willing to let that happen. I guess I could have put that over here as well. Of course, here, your entire velocity is in that direction, with or against the field line. Now I have to acknowledge the fact that one component is used for one purpose, for drift. I guess I can call this drift. And the other component is used for circling. So circle plus drift equals helix. Those are the different possibilities for trajectories. Okay. Let me try to give you some evidence of this drift. I'm going to have a demo. You may even have the ingredients for this at home. So here's what I have. I have a battery, which hopefully is not expired, because then this won't work. And what I have a nail, and I put that nail on a magnet. Okay. So, we'll of course talk about how magnets work a little bit later, but for right now, of course, the purpose of the magnet is to provide the magnetic field. Okay, so there will be a magnetic field where this nail is, right? It also happens to magnetize the nail itself, so it'll allow it to stick to the thing like this. So then what I'm going to do, first of all, I'm going to put a little flag on here, so for those of you that are in the back or watching this video can tell what's going to happen. So that's just cosmetic, so you can tell what happens. So I'm going to stick it on there. And now what I'm going to do is I'm going to send some particles through the nail. The way I'm going to do that is I'm going to send a current. So that's why this is a battery, because I can put one wire on top here, and I can connect it down here. It'll send a current from the positive terminal up through the nail into the negative terminal, right? Now, we of course learned that it just flows through the wire, goes up, and it's done. But remember that these particles will be subjected to a magnetic field too. And one of the things we've learned is that if you have a charge that's trying to move, if it's subjected to a spiral instead, then, or if it's subjected to a magnetic field, it can make a spiral or a helix. So let's try it. See that? Circling. What's causing that? What's causing it is as those charges try to go up through the nail, they are taken in a helix. And of course, they're not moving through free space now. They're going to bump into things. And so they're going to grab those fixed atoms in the nail and make the nail go around with it, right? So that's why you can actually see that spiraling. So let me try it again here. And try to get it, make good contact. If I can do this, I can get it to go pretty fast. See it? Okay. So you can make that at home. You probably have this little piece of wire. Get a nail or screw that can be magnetized, and just a magnet. So this just happens to be a powerful rare earth magnet. This you don't need if you're looking at it. You can tell if it's spinning if you're looking at it up close. You're welcome to try it if you want to after class, or your lab instructor can also let you have a go. Okay, are there any questions so far? Okay, so this is a bit of a survey of all the different things that can happen to a charged particle in a magnetic field. I guess I should mention, I probably should have done this earlier, but I've been dealing with only positive charges. For negative charges, as you can probably guess, everything happens the opposite way, right? So whatever a positive charge wants to do, a negative charge wants to do the opposite. So I should mention for a positive charge, use the right-hand rule. If you have a negative charge, the force is opposite to that. So I'll give you two options. You can use whichever one's your favorite. One of which is, of course, option one, is to do the right-hand rule and then reverse your answer. So basically commit to always using your right hand, and then remembering, oh, okay, I did my slap rule, I got my forces up. Oh yeah, it's a negative charge, forces down. Okay. That's option number one. Option number two, we already pointed out that if you accidentally use your left hand, then you will get the opposite answer. So slap like that, you'll get the opposite answer. So that is a mistake if you're trying to do a positive charge, but it's a feature, not a flaw, if you're trying to use a negative charge. So you can't use your left hand. So in some sense, positive charges are right-handed, negative charges are left-handed. Now, of course, they don't have little hands or anything like that. It's just the mnemonic we apply to them. Use one of those options, whichever one calls out to you, whichever one is less arthritic perhaps. Just don't do them both, okay? Because of course, if you use your left hand and then reverse the answer, you're going to get, it's kind of a double negative, right? You end up with the wrong answer. So either right hand rule and reverse your answer, or the left hand rule, not left hand rule, and then reverse the answer, because that's going to give you the same result as for a positive charge. Okay, so any questions on that before we move forward? Okay, so I guess let me do one more device that just uses this. This is called a velocity selector. I think you have one of these on your homework. As to why it's called that, I'm going to not touch it right away. But here's what we have. We have a region of space in which there is a magnetic field. I'm going to do that in red because there's going to be a couple different things flying around, and I don't want to mix them up. And there's also going to be a parallel plate capacitor in the same region with the plus charge on top and the minus charge on the bottom. Now you should be able to look at this and say, which way does the electric field point from this thing? What does the electric field look like between them? It's down, right? So I'll do that. Let me do that in a different color. The electric field's going to look like this. So we have a magnetic field that's into the page and an electric field that's downward toward the floor. I'm going to, into this region, I'm going to fire a particle, a charged particle. So let's work out, based on that, what are the two fields, how are they going to influence that particle. So let's start with the magnetic field. We'll do our good old slap rule. So we point our fingers along V, decide how to orient our palm. Palm is going to have to slap V into B, which is into the page, V into B, so forces up, right? The magnetic force will be up. What's the direction of the electric force? Electric force. Down, because positive charges feel a force with the field. And so we find that the two forces exerted by the two fields are opposite, and that's not an accident, that is purposeful. If those forces are oppositely directed and they happen to exactly cancel each other out, what is the motion going to look like? It's just going to go straight ahead, right? Newton's first law. So it's going to run the gauntlet like that. So then the question becomes, under what conditions can those two forces cancel? Well, let's solve. When is FB equal to FE, which is to say that the net force is 0, we can plug in our two force laws, QVB sine theta and QE. Okay, so what do we put in for theta? What's the angle between the velocity and magnetic field? 90. Sine of 90 is 1, so we get maximum amount of force there from the magnetic field, right? Because we're cutting directly across the field lines. The other interesting thing that we notice is that there's a Q on both sides. So the Q cancels. And then we solve for this. V equals E over B. So in order for the charges to experience no net force, they have to have just the right speed. That's why we call this a velocity selector, because this thing will only let things at a certain speed get through undeflected. And that speed that it selects for is actually the ratio of the two fields. Now you may not remember, you may not believe that the ratio of the electric field to magnetic field is actually meters per second, but let me remind you that this is newtons per coulomb, and this is newtons per coulomb meters per second, so that's the only difference, right? So only charges with this exact speed will come out of this gauntlet undeflected. That's why we call it a velocity selector, because we can oftentimes have control over the electric and magnetic field strengths, so we can tune those to filter out whatever velocity we want. Okay? So we should probably take a look at what happens if you're going too fast or too slow. What happens if the speed is greater than that? Well, if you're going faster, the electric force could care less, but you will exert a stronger magnetic force, right? Because magnetic force is velocity dependent. So what happens if you have this force is larger than this force? How is that going to move? It's going to curve upward, right? So it may hit the top plate here and not make it through. Now if you're worried, well, what if it makes it through the end, but just kind of more toward the top plate? Let's put in a little barrier here with a little hole. And if you get deflected even slightly, you'll hit the barrier and instead of making it out the hole, right? Likewise, if you're going slower than this magic speed, this speed that is just right, this Goldilocks speed, I should say, well, again, the electric force is not a velocity-dependent force, so it does not care how much force, or it does not care how fast you're going. It's going to exert the same amount of force regardless. But if you're going slower, what happens to the magnetic force? It's smaller, right? In fact, we learned that in the limit that you're stopped, the magnetic force disappears entirely. So how is that going to move? It's going to be deflected downward. It'll either hit the capacitor plate, if it's really severely deflected downward, or it'll hit this barrier somewhere, okay? So this is an amazing thing. We could send some complete random assortment of speeds through there, but only when it select out all particles going at one speed. The rest of them won't make it through. Now, the only arbiter for what makes it through is speed. So we should probably take a look at what happens if we increase the charge. So what happens if the charge is bigger? Well, if the charge is bigger, certainly the magnetic force is bigger, but so is the electric force, because they both depend on charge. You can see here that it cancels out. If you, for instance, have a charge that's twice as big, that's just going to double both forces, but they still cancel, right? It doesn't even depend on the sign of the charge. The charge can be negative. If the charge was negative, well, both forces would reverse, but they still cancel, right? So that would mean that the magnetic force was downward now, but the electric force was up. So they still cancel. So the amount and sign of charge are irrelevant. The only thing that separates out is speed. And of course, we're drawing a wedge between what matters for one field and not the other, right? So the speed does not affect the electric force at all, but the speed is going to greatly affect the magnetic force. So that's why speed is the one tiebreaker, okay? The charge cancels because it matters to both. So the amount and sign of charge is irrelevant. The only tiebreaker is that speed is on one side but not the other, and that's why this ends up working. Okay, are there any questions on that? Yeah?
When is this useful?
I'll talk about that probably, I don't remember when, but if you can imagine having a whole bunch of ions, right, that are flying around at different speeds, and you want to create ions at just a single speed, right? You can use this, for instance, this was used in World War II to to build a nuclear weapon. So I'll talk about that, I guess, in the next couple lectures. So obviously, you know, one useful thing for this is to control for the speed of charged particles. So sort out what might be an assortment of speeds and get out only a single speed. Okay. So I think that covers it for single charged particles flying around. But, of course, we've gotten accustomed to not just single particles flying around in free space, like on homework number 2, but what if you have a whole bunch of free charges and they're moving along a wire? It's a current, right? So what might we do here for that? So we want to find the magnetic force on a current carrying wire. So how is this different? Not really very different at all. In fact, it's going to take us all of a couple minutes to do this. Let's say I have my magnetic field like this. I have my charged particle like that, but it's joined by a bunch of friends in a wire. And let's say that this wire segment is of length L. So let's go ahead and write down the formula. The magnetic force is equal to QVB sine theta. And then for the speed, I'm just going to substitute in that the speed of the particles is such that they traverse the length of this wire segment L in a time delta t. So I go ahead and put that in there. And then, with one fell swoop, I'm done. Instead of grouping the time it takes with the length, I'm going to group it with the charge. So we can talk about the charge and the time it takes to traverse, and talk about charge per time, which we call what? Charge per time, coulombs per second?
Amps.
Amps. It's current. It's the electrical current in the wire. So just like that, we have a formula that doesn't require us to get down to the individual charge carrier level. We just have the total current in the wire, the length of the wire segment, the field that it's in, and the sine of the angle between them. And just so that we don't have to get down to the individual charge carrier level, of course, the direction of the electric current is the same as the direction of the charged particles. So we can call this instead the angle between I and B. So this is our formula for the size. And then the direction is once again the right-hand rule, where we're now going to slap I into B. So instead of the velocity of a single charged particle, we slap the direction of that they all are moving in. So slap I into B with your palm of your right hand. And then your thumb gives the direction of the force, which should be perpendicular to both of the other two. So in this case, I guess let's practice. I slapped into B, I, B, force is going to be into the page. So on this particular wire segment, it's going to be pulled into the page. It's the exact same right-hand rule that we had before. And so if you go over here to my demo that I showed you earlier, you may notice that this was labeled not just V for a single particle, but it says or I, right? So it says you can be either a single charged particle moving in that direction, or you can be a bunch of charged particles moving in that direction. This, by the way, is even simpler because current is, of course, always made out of positive charges, right? So for a single charged particle, we could have positive or negative charges, and we have to remember to reverse the answers. But in this case, current is always made out of positive charges, so there's no negative version to remember. Okay, are there any questions on that? Okay, so this is a little bit weird because it's, of course, this disembodied segment of current. Charge needs to come from somewhere and go somewhere. So this is just really a building block for assembling something out of these segments. So the next thing we're going to take a look at is what about if the current is flowing in a loop? That's usually the case for us, right? Current flows around, right? Like in a circuit or something like that. So let's go to that. So what about a current carrying loop? So now let's assemble something like that. So I'll go ahead and put the magnetic field as being into the page. Let me just say it's uniform so I don't have to draw those everywhere and just kind of gets annoying to clutter up the diagram. And then let me construct a 4-segment current loop. Not sure how far we're going to get with this today, but at least we can practice the right-hand rule. So let's start with the top segment. I points to the right. I want to slap it into B. Forces up. Okay. I slapped into B. So force is like that. I guess let's do the bottom one next. I points to the left. When I orient my palm, B is into the page. I seem to have focused a lot on that today. I guess you should do some other examples next time. I slapped into B. I slapped into B. Forces down. Hopefully not shocking if we're comparing the top and the bottom segment, right? Because the only difference between the top and the bottom segment is that the current's flowing in opposite ways. And if nothing else changes, then the force is going to be opposite ways. Let's try the side one, the right side. Point I down, so fingers down. Slap it into B. This is getting a little bit arthritic, so you rotate your page if you need to. I slapped into B. Forces to the right. That force will actually be a little larger, so I should draw it a little larger. Even though it's the same current in the same field, why is it larger? I've tried to draw it. It's longer, exactly. So this is larger because the force is also proportional to the length. So it's proportional to the length. That's a little bit longer of a side, so the force is a little bit larger. Just to spare you the suspense, same amount of force, but in the opposite direction the other side. Make sure you can get that with the right-hand rule. So if you look at this, what does the net force appear to be? 0. So the net force is 0. The reason why is because the forces on opposing sides cancel. So you might think, well, wow, the current carrying loop is pretty boring. Nothing happens. Okay, net force is 0. So we'll find, of course, that that's not the end of the story. So let's pick it up there next time. We'll find out what's so great about a current carrying loop. In certain ways, this is actually what we're building up to. This is where all the action is. Okay, so we'll start next time.